So in our last set of notes, we were talking about looking at this one quantitative variable, and remember we're doing the same things with a quantitative variable that we did with a categorical variable. So in the last set of notes, we looked at describing both numerically and graphically a quantitative variable, but then we also let in the idea of a sampling distribution for a quantitative variable. But the main goal when we talk about that sampling distribution is really to build into more the inferential side of things. And by that, again, I just mean the idea of a hypothesis test or a confidence interval. So in this set of notes, we're going to talk about how we do hypothesis tests and confidence intervals for a quantitative variable. So we're going to be building off the last set of notes where we talked about the central limit theorem, and we learned that under certain conditions, so if we had our relatively random and unbiased sample, and we had either we knew things were normally distributed to begin with, or our original histogram looked symmetric and bell-shaped, or if we had a sample of at least 30, then we were able to say that y bar, our sample mean, would be approximately distributed normal with a mean of the population, mean of mu, and standard deviation, which was sigma over the square root of n. Once we knew that happened, then we were able to use the z formula to calculate probabilities. And so how we found our z is we took what we were interested in, which was y bar, subtracted off its corresponding mean, which was our sigma, or our mu that we had right here, and then we're going to divide by our standard deviation, which was the sigma over the square root of n. And so that's how we found a z in the last set of notes. But again, so our main goal here is leading into hypothesis testing, leading into confidence intervals. There's a problem with what we were doing, and what this problem really is sigma. So first, just remembering what sigma actually is, right? This is our population standard deviation. So why is this such a problem? So let's go through first the idea of a hypothesis test. So when we perform a hypothesis test, we will have a rough idea of what to use for the population mean. So for our mu. And the reason we'll have that idea is we're going to have this idea of a null hypothesis, so we're going to have a rough idea of what number we could use for mu. But since we're doing a hypothesis test, we're not actually going to be sure about it. Right, that's kind of why we do a hypothesis test in the first place. We want to say, well, maybe is it bigger than that, maybe is it smaller than that, or just something different. So even though we have a rough idea of what it is, we're still not going to be sure about it. Now when we do a confidence interval, so think about the idea of when we did a confidence interval before. So we did a confidence interval back for a categorical variable when we didn't know what p was. If you remember, p was our population proportion. So when we do a confidence interval here, just like we didn't know the population proportion, I'm not going to now know the population mean. And the reason I'm not going to know it, because that's actually what we're trying to find. So I'm not going to know mu for sure then. So, I mentioned that the standard deviation of the population is our problem, but I keep here talking about the mean. So here's sort of why that is actually important. So if we are uncertain of the mean, mu is our mean, then there's no way that I know what sigma is. Now, why does that mean I don't know what sigma is? So sigma is our population standard deviation. But remember how we describe that idea is that sigma, or our standard deviation, is the typical distance from the mean. So if I don't actually know what the mean is, I don't even know where to go out that typical distance from. So there is no way I can know the standard deviation of the population if I don't know the mean of the population. There's just no way around it. So before, when I look above, right, so we have this z that we already have above. So what can I do about this? Well, a probably good idea, which would at least seem reasonable, is if I don't know sigma, I can replace that with S. And do you remember what S was? S was our sample standard deviation. So what I'm going to do instead is I'm going to have my y bar, my mu, and where I saw sigma before, I'm just going to replace it with S. That seems hopefully like a pretty reasonable replacement. Now the thing that I have to worry about is once I do this, this is not the same thing. Alright, so I'm actually not going to be able to call this Z. This is actually what's called a T. So this is what kind of drives us to the point, and then I talk about, well, what is a T? What is a T distribution? So the first thing I'm going to do here is actually draw the Z that we're used to. Alright, so this is what we're used to seeing. Right, that's going to be our Z. And Z was centered at 0, remember, because the mean was 0 standard deviations from the mean. Now what the T is going to look like, I'm going to try to make sure I draw this pretty well for you, so I need to have a target to go for. Is it actually looks a lot like the Z. So let's talk about what's the same about it and what is different about it. So this is first my visual for you. So usually I tell students to picture their perfect Z distribution. And then imagine that someone came and sort of sat on it. So I generally think of describing to students that T is basically a Z that's been sat on. So that's my visual description. So what do I mean by that? So things about this. T is symmetric and unimodal. Which was also true of a Z. T is also centered at 0. Like Z is as well. So in a sense, at first when I'm drawing it, man, T doesn't really feel very different. So what I need to have is how is it different? So T has a larger spread than Z. And more specifically with it, the spread changes based on a new term here of what's called degrees of freedom. and that degrees of freedom will usually get labeled as a DF. Now, so first to try to understand why my spread, first of all, is larger, and then also why my spread changes. Well, the spread is larger in a sense because we had to estimate this population standard deviation, right? I'm taking this sigma, which is a population value, and I'm replacing it with a sample value. So just kind of due to my uncertainty of replacing a population value with a sample value, it makes me have a larger spread, or in a sense be a little bit more unsure of my answer. Now, why it actually changed with this thing called degrees of freedom. So sigma was our population standard deviation, but S is the sample standard deviation. So we're calculating this based upon our data. So if I have a data set with only 10 values in it versus a data set with 100 values in it, and I'm calculating a sample standard deviation, I'm going to put a lot more trust in my sample standard deviation when it's from 100 observations and not just 10. And so what we find is this degrees of freedom that changes the spread is related to our sample size. So the sample size does affect this spread because of the idea of I'm taking this population number, replacing it with a sample number that's based upon a certain number of observations, and how many I sample is going to tell me how much trust I can put in that number. And so what you're going to see happen as we dive in to a hypothesis test next time is that we're going to be looking at this idea of how a t is going to be used instead.